And I am live. That is nice. Today is 1st of October 2025. Wednesday. Shit, yes, I should have known that without looking at the date. So today is 1st of October 2025, Wednesday. Shit. And today we are going to do graphs, and that is a nice thing. And more specifically, we will be using CPHB Competitive Programmers Handbook, and we will see what these things are. The algorithms, there are three algorithms for finding the shortest paths in graphs, and the goal is going to be to understand and implement at least two of these, them being Bellman-Ford and Dijkstra's algorithm. Dijkstra's is supposed to be greedy. Someone in the chat said that earlier at some point. So the goal is going to be these two algorithms at least, and if we could, like if it is possible, then we will also get into this and also implement these algorithms and solve some questions. I think there must be questions for finding the shortest path. Yes, this one uses, and yes, I don't know about Bellman-Ford, but we can use Dijkstra's algorithm when the source is fixed, and Floyd-Warshall when the source and targets are variable. And Bellman-Ford, I don't know. We'll have to see. So there are n cities and m flights connections between them. Your task is to determine the length of the shortest route from a source city which is fixed to every city. So this one is going to use Dijkstra's algorithm, and this one, there are n cities and m roads between them. Your task is to process q queries where you determine the length of the shortest between two given cities. So that is going to use Bellman-Ford, and we will have to see what this, no, the other one, shortest route second, is going to use Floyd-Warshall, and we will have to see what Bellman-Ford does. So let's just get into it, right? Cool, cool enough. Shortest paths. Finding a shortest path between two nodes of a graph is an important problem that has many applications, practical applications. For example, a natural problem related to a road network is to calculate the shortest possible length of a route between two cities, given the lengths of the roads. And this is what Google Maps uses to find the best routes possible. And those routes sometimes go through a river or something. In an unweighted graph, the length of a path equals the number of its edges. The length of a path equals the number of its edges when the graph is unweighted. That makes sense. And we can simply use BFS. Yes, that makes a lot of sense. If the graph is unweighted, we can just use BFS to find the shortest path. That makes a lot of sense. However, in this chapter, we focus on weighted graphs where more sophisticated algorithms are needed to find the shortest paths. Okay, with that, let's go. Bellman-Ford. The Bellman-Ford algorithm, there is something written about it. One, finds the shortest paths from a starting point node to all nodes in the graph. The algorithm can process all kinds of graphs provided that the graph does not contain a cycle with negative length. Okay, the algorithm can process all kinds of graphs provided that the graph does not contain a cycle with negative length. Okay, so there cannot be any cycle, and if there are cycles, then Bellman-Ford does not work. And one more thing, that Bellman-Ford does the same thing that Dijkstra's algorithm does. So in this question, we can apply both of these algorithms. But in this question here, the source is not fixed because you will be given queries, which would be city 1 and city 2, and find the shortest path between city 1 and city 2. So here the source is also moving, so we cannot, like, that is messed up. But in this one we can use any of the algorithms. Yes, we can here use Dijkstra's algorithm or Bellman-Ford. That is cool. And therefore, our goal is going to be complete this question with both of these algorithms one by one. First with Bellman-Ford and then with Dijkstra's algorithm. And what do we know else about Bellman-Ford? That it should not contain a cycle with negative length. And let's read more because I have a doubt here, and that is negative length. Like a path having a negative weight, this algorithm will not work if there is a cycle, first of all, and second, if the cycle contains a negative length. Well, I think that does make sense because if there is a negative length, then maybe the algorithm keeps looping over it again and again and again, and we go through the same nodes again and again to reduce our overall time, I guess, length. If the graph contains a negative cycle, that makes sense. A cycle cannot be negative. The whole length of a cycle cannot be negative. Only then the algorithm will keep looping over it, and we will go to the same place again and again and again in order to reduce the total length. That makes sense. So, cycle cannot have a negative length. That makes sense. The algorithm keeps track of distances from the starting node to all the nodes of the graph. Okay. Initially, the distance to the starting node is 0. Okay. And the distance to all other nodes is infinite. The algorithm reduces the distance by finding edges that shorten the paths until it is not possible to reduce any distance. The algorithm reduces the distance by finding edges that shorten the path until it is not possible to reduce any distance. Okay, that would make more sense, I guess, after we see some examples. Let us consider how Bellman-Ford works on something like this. So this is our initial node. That is why the distance is 0. And all the other nodes have a distance of infinite from the starting node. And now what? So let's theorize a little bit. And the theory is that we will go through all the edges and we will also keep track of the shortest distance to the current node and what edge we are taking, and we will see if after taking this edge we will update the shortest distance for this next node that we are going to go to. And the shortest distance, wait, shit, okay, this is bad in a sense because, and this would have to use BFS, this cannot use DFS. No, that is even bad because let's say this 2, let's say we went to the 2 first by this route, and the shortest distance of 2 reduced from infinity to 11 to 10 because it is 7 plus 3, 10. And then from 2 we went to 6 and we updated the shortest distance for 6 from infinity to 10, the shortest distance to get to 2, and plus 2, the length of this edge. And the shortest path to get to 6 is now 12. But then we went to 2 again and we updated the path here, the shortest path from 10 to 5. But then we should also update the path for 6. I guess if we see that ever we are getting to a node with the current path being smaller than its current shortest path, then we will call our algorithm or whatever we are using, DFS or BFS algorithm, for this node again. And that makes sense. That does make sense. Each node of the graph is assigned a distance initially. I think without even, okay, let's go to the through the theory for this thing, and without going through the implementation, we will implement it on our own, and that would be pretty nice. Each node of the graph is assigned a distance. Initially, the distance to the starting node is 0 and the distance to all the other nodes is infinite. Yes, we did saw that. The algorithm searches for edges that reduce distances. First, all edges from node 1 reduce distances. Okay, we are searching for the edges which reduce distances. Okay, after this, edge 2 to 5 and 3 to 4, 2 to 5 and 3 to 4 reduce distances, and from those edges, from 4 to some place, we will call the algorithm again. After this, edges 2 to 5 and 3 to 4 reduce distances, which is this 2 to 5 and 3 to 4. Finally, there is no more change because this is the updated edge, and if from this we can go to here, here, or here. And yes, first of all, we will not go back. That is one thing. Yes, we will not go back. How do we make sure that we do not go back? Fine. And shit, we also have to return the path here, right? No, we just have to return the length of the distance. The length what is given to us. The first line contains N and M, the number of cities and the flight connections. There are cities numbered from 1 to N, and city 1 is Sirgiala. What is that? City in Finland? Shit, that is something somewhere. Okay, anyways. After that, there are M lines describing flight connections. Each line has three integers A, B, C. The flight begins at city A, ends at city B, and the length is C. Okay, you can assume it is possible to travel from Sergiala to all the other cities. So to go from Sergiala to Sergiala, the answer is 0, and to go to city number 2, answer is 5, and to go to city number 3, the answer is 2. That makes sense. We have to make sure that we do not go to the city that we just came from. Okay, that also makes sense. And right. So whenever we see a edge reduces a distance, we will call our algorithm from that edge. That makes a lot of sense. But we have to make sure, okay, we will never go back to this starting edge. That is one thing. But we also have to make sure that, okay, yes, yes, this makes sense. I was thinking that when I'm here, I might try to go back to this city and I would say that the distance to get to this city is 1, but that is not the case. The distance would be the weight of the edge plus the current distance for the current node, the current ith node, and that would be 5, which is higher than this. So we don't even need to keep track of a visited matrix in which we would have 1 for all the nodes that we have visited. That makes sense, right? Finally, there is one more change. This one from 4 to 6, and yes, that is true. After this, no edge can reduce any distance. This means that the distances are final, and we have successfully calculated the shortest distance from the starting node to all nodes on the graph. For example, the shortest distance 3 from node 1 to node 5 corresponds to the following path. Okay, path also is something. Path is also something. Yes. And now implementation. We will not read the implementation. We will do the implementation. First, let me clean these things and clear tmux set. Tmux build server, my bad. Tmux set, tmux attach, target T, CACS, right? And we will go to graphs and start new Vim. And the question that we are doing now is this one. And we will apply Bellman Ford to this. Hello, how's everything? And right now we are learning the shortest paths to go from a place to another place. And the name of the title of the video is There is a Narrow Way, which is a reference to something, and it is a nice reference. N and M. And then we are going to store these things in a matrix list, in a adjacency list, a representation. ADJ. N is going to be the number of nodes, or n plus 1 seems more like it, and a empty vector. L comma R for int I equals 0, I less than n, I plus plus, C in L, P in R, and ADJ, L dot pushback R, ADJ, R dot push back L, and we will have our algorithm here. Yes, and we would need a few things. Vector n, we will call it this thing path p. And when we do know the size, we will do p dot assign n plus 1 dot 0, or not 0 but int max, because that is what the initial path is going to be. Yo, solved 3 today and continuing. Yes, keep on moving forward. Continue. And we will update the path for 1 to be equal to 0, because false, yes, 0. And then we will call our function, let's call it Bellman Ford, and this function is going to take in a vector of integers, a matrix of integers called ADJ, and the initial value I. And now a few things are going to happen. For int I, for int x n ADJ I, for every node, that is for every node, yes, that is, and shit, we messed up big time. This is not going to be an integer, because we also have weights. So how do we store something like this? Let's use a pair. Is a pair going to be good, where the first value is going to be the next node which this edge connects, and the second value is going to be the weight? And let's go with that. That does seem feasible. W, and since weights can be very big, let's make this thing a long, and here we would also have to take in the weights, and here R and weight, L and weight. And this might be bad because we have the same thing stored twice at two different places. This might be bad, couldn't say. But anyways, with the, yes, but this is much better than matrix representation. Right? In our matrix representation, our size, the data that we are storing, is going to be always, no matter how many edges there are, it is always going to be n square space complexity, and that is bad. And I think this, the representation that we are using right now, adjacency listed representation, it is much better than that. So we have to change this also for auto x w in adj I. That is for every x node that is connected to the ith node with the edge of weight w. And if the shortest path, now the current path to get to w to get to x is this one px, and if the current path is greater than the current shortest path to get to x is greater than what would be the path if we get to x through I, and the path to get to x through I is pi, the shortest path to get to I plus w, the current, the weight of the edge that is connecting these two things. If that is true, first of all, we will update px equal to pi plus w, and we will call Bell-Manford. I am pretty sure that the spelling is wrong. It has double L. Bell-Manford. Substitute Bell with Bell. Bellman-Ford. Call this ADJ with X. That is very nice. And we can expect our path to be filled by this point. For int I equals 1, I less than equal to n, I plus plus, C out, Pi, space or a new line, I equals n. When I equals n, we output a new line. When I is smaller than n, we output a space. That didn't scale out, and there is a reason. Yes, yes, this thing. This has to be a pair of integers, and since this is a pair of integers, we will say 0, and yeah, that should be enough. That is wrong. Of course, it is wrong because when we add something to int max, it overflows and becomes negative, and that is not good. So we should not do that. What can we do instead is w, we can make this long. Yeah, we can make this thing long, and this should work now. This should have worked now. Okay, let's change things to long. Substitute int with long on the whole line except the part where we are using the index, and we would have to do the same thing here. Substitute int with long on the whole line, and this should work. Wait, now that is strange. Of course, because we are never calling the function, because we are never calling the Bellman-Ford function, of course it is wrong. So we don't even have to change things to long. This line would work. We just have to call the function after this, and that is Bellman-Ford ADJ starting from node 1, and now it does work. That is pretty nice. Bellman-Ford, it like it's a very basic algorithm. So it is not difficult. It is very basic. Okay. And this should work. And but before submitting, of course, we will have to rewrite the whole thing again. N is the number of nodes, M is the number of edges, and we will take in N and we will take in M, and we will also have a global vector called P, which is going to store the shortest distances to the ith node. And when we know the number of nodes, we will assign ASI gn assign size of P is going to be n plus 1, and all the values are going to be int max. And then we will take L, R, and weight. Now we are going to fill our data structure, which is a adjacency list of not integers but pairs. ADJ size is n plus 1, and we are just going to initialize the internal vector like that. And we are storing this as a pair where the first value is going to be the next node that this current edge connects to, and the second value is going to be the weight for int I equals 0, I less than n, I plus plus, take in L, R, and weight, left value, right value, and weight. And ADG L dot push back a matrix connecting to R, a matrix edge connecting to R with weight W, and do the same thing in R connecting to L with the weight W. And after that, we say the path or the weight, the distance, minimum distance to get to 1 is 0. And then we will call our function called Bellman 4, which takes in this strange vector, vector, pair, int, reference, ADJ, data structure, and I. And we will, yeah, we will just after that auto x w adj I, which just means that this current node I is connected to this node x with a edge whose weight is w. And if the current shortest path to get to x is greater than the distance it would take to get to x from I, which is the shortest path to get to I plus the weight. And this thing should be long because a lot of pi can be equal to int max. We do not want to mess that up. And if that is the case, then we will first of all update px to be its shorter equivalent. And then we will call the Bellman code function on this x, and that is about it. Here we will call Bellman 4 with the graph data starting from node 1, and then we will output everything I less than equal to n, I plus plus, C out P path to get to I, and we will update, we will then output a space or a new line depending on I's value. Should work. Okay, I messed up here. This should be DJ, and that does work. We can just submit it and it is going to work. Good morning. Hello. I use namespaces. Of course, we are competitive programmers. We use namespaces. EDZ might be better. Yes, that is I was wondering. To be global as well. Okay, though it uses more memory. Here I am using a reference, so I thought it might be better, like not as bad as sending it directly. And very annoying to write once you start doing DSU, having to have to pass in multiple vectors to functions. Okay, that makes sense. That makes sense. So I should have better like ADJ, better habits. I should have good habits. And also, is there a better way to store this? Because we also have pairs. So we also have weights. Edges also have weights. So I'm using a pair here. I don't think there is a better way than this. No, gonna get errors. No, just because of an spelling mistake. Spelling mistake. Yes, there was a spelling mistake. And let's do an edge list and traverse it both ways in your BF function. Edge list. Okay, what is the edge list representation? Ah, okay. We are using adjacency list, and we can use an edge list and traverse it both ways in your BF function. Bellman-Ford, okay, that much I do get. Bellman-Ford BF function. And DSU. Should you also said DSU at some point in the past, and I forgot again what DSU is, as in vector of just A, B, W. Okay. And then how would I know where can I go to from ith node? So do I sort this thing? And what if I have the B node? And yes, yeah, it would be hard to look up. It is easier to look up what edges there are, but I cannot get over it. What you need this A to not be infinite, to be like make a path. Wait, we can use shit, that does make sense. Because here we do not care about the order. We can look at an edge and hmm, we can just look at an edge. Okay, we can just look at an edge, and if it is good, because you already have the distances. Hello. So and just compare distance after it. And if there is a particular edge which is changing the distance, then we add, how do we like make sure that the order is correct? We have to maintain a queue or something, because let's say in this example here 5 is better, like going from 1 to 2, 5 is better. But let's say this was 1 and this was 2, and we can like actually draw this, actually draw. What if we had something like this, node 1 and node 2, node 3, and this is like 10, this is 1 and this is 2. And if we were to use this edge, initially the path to get to here is 0, here it is infinity, here it is infinity, and let's say we start with this edge. And when we do, what we will even see, uh, take the current path of this thing, add 1 to this, and is it better to go to this place? I think we just first find out the edges which come from this place, and we call the Bellman-Ford function on this, on these edges, and we will see going from 0 plus 2 is better. 0 plus 2, which is just 2, is better than infinity. So we will update this distance and we will make this 2. And here also we will change this distance and we will make this 10. And then we will go through the rest. Okay, so if the starting nodes are correct, then everything is going to be amazing, fine, I suppose. because the only problem here is with the data representation. And this part is like, okay, cool. This makes sense. Making this global. And since we are making this global, we can make adj dot assign later. This should work. Key, I messed up somewhere. Yes, I did mess up. Balloon code, we don't have to give this. And here also, we just call Bellman code with the I. Okay, cool. That is working, and that does make sense. Let's see if this is like totally correct, and it would be cool. And you do not like the fact that we are using namespaces. Namespaces are amazing, like in competitive programming, because we do not have to write standard input or something, std and everything. Graphs, shortest routes first, but then shorter codes. But then you could also say, yes, yes, why not? Shit. Wrong answer on everything, of course. Shit. Before fixing this, let me say, like, against my defense, if you go to the current number one player, Jiang Li, Mr. Jiang Li from China, and if you see his submissions, any of his submission, he doesn't uses like using stdio, uses stdin, and that is crazy. He's a top level player and he uses this. Yeah, so that is like, yes, crazy. I cannot say that it makes me faster. Chinese momo. You are being racist. There is something horribly wrong with this. And I think it is because of the fact that we are using long and things. Think, I think. Int max. Instead of int max, let's divide this number by 2. That might be it. And also, we are going to use your thing. This is like so fucking amazing. This thing that this Neovim keybind that you gave yesterday. No, I'm not defending myself. I'm putting an argument against myself. Strong, steel manning your argument. Use long instead of long. Those are like, no. This using long is like gives more feel to it. And this thing, it is still wrong. 3 to 100. Okay, this is like completely wrong. Something is bad with this. What are the limits? And this C can be very big, but in this example, it is not very big. It is small. P assign n plus 1 divided by 2. Yes, int max divided by 2 also makes sense. And yes, okay. One is connected to just one city, one other city, and that is 2. So the path to get from 1 to 2 should have been 9 at least. That much should have been correct. First one is 0, and is P equal to 0 not working? P1, C out, new line, and then C out. After new line, C out, P1, CMP, copy, paste. Okay, P1 is 0, and the next thing is also 0, but this should have what? Taken L, R, and W. L dot pushback R, W. So there is something wrong. ADJ, I think we are not taking the data correctly. Here 10 appears 3 times. So 10 should have a degree of 3, and we should see 3. Okay, we do see 3. So we are taking the data correctly. There is something else which is wrong. BAF is too slow for this problem. Okay, we will update that, but I mean, we will then apply Dijkstra algorithm. Like, we will read about it and then we will apply Dijkstra's algorithm. But this is not working even for a small number. Our test case is just this much, and the answer is coming out wrong for all of them. And yes, this is slow. Time limit exceeded, 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 exceeded. Bellman Food 1. We are calling Bellman Food for 1. And current distance P is very big. I say CMP. Okay, high is not here. So we are never going inside this thing. And Y, the current path, the current value to get to this thing, and plus PI. C out, I, X, space, PI. 3. This 3 is from here. This 3 is from here. So we are not even going inside this thing, which is very, very strange. That makes sense. There is no X. 1 and 0. So we do call this for 1, and P1 is 0. ADJ I is ADJ not getting updated. How many nodes are connected to node number 1? 0 nodes are connected to node number 1. So something is messed up. I think it would have been better to cover Discra before Bellman Fort. Oh, I was just like, I don't know anything. I just came to know about Bellman Fort, and I was going through this order, shortest path, Bellman Fort, and then Discra. I haven't even read the implementation. I just read this, and now we are implementing this. Hello. Yes, after this, we will just go straight to Discra and never use Bellman Fort. Maybe, I don't know, there might be some use cases where Bellman Fort is good. And one more thing, I just got to know about segment trees, and they are pretty good. I solved a couple of questions in range queries. Like these are easy static range minimum queries, and this one, for this one we use sparse table, static range minimum queries, and for dynamic range minimum and some queries and minimum queries we can use uh, uh, segment trees, and that is pretty nice. Segment trees are pretty cool. And I haven't gone through the whole thing about segment trees from this book, but they are saying this is a general data structure which we can use for a lot of things. And there are also optimizations. This is more like dynamic programming. We can use this for a lot of things, just like dynamic programming. And that is why people like prefer reading about this and not reading about Fenwick trees. Uh, yeah, like binary index trees. And because binary index trees are very specific, they only help in getting dynamic sum queries, but we can use segment trees for anything we want. They are a general data structure. Yes, it is very amazing. It is working amazingly. And today we are going to read this thing, shortest paths. And the target is at least to get to know Bellman Ford and Disra, and we will see what we can do about flood watch. Yes. Okay. What was that thing? Square root decomposition is another cool algo to solve similar. Shit, I've heard that thing. Square root decomposition. It is, I mean, of course, it is on CP algorithms. CP algo, square root decomposition. Hmm. Okay, there are just a lot of things. Let me actually write it down. Wait, I will take a screenshot. Yes, I'll read it. And now to this thing. So we are not taking in the data correctly somehow, because here I am outputting what is the degree of node 1, and it comes out to be 0. Like that is crazy. Why is it 0? This doesn't make sense. And I just cannot say how good the keybind is that you gave yesterday. It is amazingly good. We can find standard problems for particular topic. Just CACS, that is the best thing. Go to CACS, find the topic that you want to practice. Introductory problems, sorting, searching, dynamic programming, graph algorithms, range queries. Amazing. CACS is pretty cool. Amazing. And like assistant UM, I wanted to write a compilation time checker like, okay, but I guess I'm not that good at shell scripting. Which, why would you need shell scripting? Can you not do that using Lua? I think assistant NUVim also does this in Lua. I do not know, but you can see assistant NUVim shell scripting. So you were thinking about calling a function in shell that would calculate the time. Wait, shit, maybe you can. Yes. So when you call the compilation function and then run the binary and then end when the execution ends, that is known by the shell. So you want to know shell scripting. Maybe you can go to learn X and Y minutes and PowerShell, not PowerShell shit. No, that is bad. Do not go to PowerShell. Bash. You can go here, Bash, or there is a YouTube channel, Bash Bunny. Maybe you can watch that. But yeah, this is more preferred. Bash, if you are using ZSH, there must be a ZSH thing. No, it is not a scam. I started C++ from this website only. So this is not a scam. Scripts, my minitest.lua. Docs. Yeah, yes, getting back to the problem. This is messing up. Internet. LRW. How is this thing messing up? Maybe, maybe. And yes, just your keybind is amazing. It is working amazingly. Okay, it is still wrong. There is something still bad. No, no, it is not a scam. If you want to contribute and make it better, you can contribute. That would be better. We are not seeing this high, and we are not even seeing this thing. Yeah, they're not seeing anything. Yes, we are going to use printf, %d, comma, %d, comma, %d, new line, L, R, W. we see 1 and 2 are connected by a edge whose weight is 9, but we don't see that particular edge here. We see 5 and shit, of course. Do you see the bug? Does anyone see the bug? Shit. We can remove all of these statements because the bug is in plain sight now at this point. And if anyone can see spot it, let me point it out. And also my stupidity. This has to be M because there are M number of edges, not N number of edges. Ah, and the answer turns out to be correct. Now, shit, the first shortest things are 9, 11. Okay. And we can submit this again. And it works hopefully this time. And also this might give English is weird language. English is a weird language. Palpable. That is the word I learned today. Palpable. Labyrinth, shortest path, 1. And this might also give us time limit exceeded error because someone said, Eric said, "True." Shit, this is bad. Shit. How's this wrong? I might be not implementing this correctly. Might not be implementing this correctly. The test one here is different from the one that is given in the example on the question page. That is why these two tests are different. Routes are one way. The first input has this and this. After that, a a flight a flight begins at city A and ends at city B. Hmm. Hmm. Shit. Okay. Well, actually, this makes this data structure pretty cool. We can just do this, remove that line, and we will be happy. So this is a DAG, if I'm correct, if I may. And now the answer is actually correct. Directed acyclic graph. Routes are one way. Thank you for that. This is the first question in which I have encountered the edges are one way. So yeah, shortest routes 22. Okay, wrong answer. Time limit exceeded. We can let go, but wrong answer. Maybe because of this. I am using here long long. Well, now we don't have to use long long because P is long long. That is the only thing I'm think might be causing this error. This is the only time that we are adding weights, and in both the cases, the thing is converted into long long. So that is cool. Yeah, seems like it should be correct because wrong answer. Yeah. And if we get time limit exceeded, we can let that slide. Good morning, yo. Not yet. First, we will go through graphs, shortest route algorithms. Is it okay? Wrong answers. It can contain cycles. It can contain cycles. Mm. But if it does, then our path will like not go there. Thank you. Okay. Study compilers. Bro has to study compilers. Crafting compilers, I guess. Crafting interpreters. It doesn't affect the answer, but your graph can still have cycles. Ah, so it is not a DAG, directed basically graph. That makes sense. That makes sense. That is true. I was lying. My bad. Six. And also it is taking a lot of time. Compiler report we can ignore. And it is your ethic to not look at the test cases. Is DP needed to solve 1500? Yes, I would say when I was solving 1400 problems, there was DP required and also in 1500. So it is nice to have. So yeah, you can go and solve maybe at least the basic problems like coin change. And you can watch Ericto's video. He has amazing videos on coin change. And also there are a couple other YouTube channels which have DP videos with animation and things. Make a small server from scratch for gathering resources. Okay, so where will you host it? But you are so TCP connections and everything. There is a nice book about TCP uh, and IP version 2 book or edition 2 TCP IP Illustrated Volume 2 Illustrated Volume 2 PDF. Yeah, I just really want to read this book. This is an amazing book. Yes, I might. Yes, that is a pretty nice book. No, I removed the PDF part. That is why I removed the PDF part. Mm, Bellman Ford call on X and path is also like non-cyclic. That is good. It can be cyclic, but cycles are non-negative. That was the one limitation here. Cycles have to be non-negative. The weight of a total weight of a cycle is non-negative, and it is non-negative because C is always positive. Okay, let's look at where we got the wrong answer. Okay, our answer is smaller than this one. That is a shit. That is almost at the limit. That is 426 million. This one is cool. Into maths. Yes. Shit. Yes. Yes, into max, into max. Yeah, I think that is the mistake. 1, 2, 3, 1, 2, 3. Yes, this is half of into max. Yeah, that must be the mistake. Monsters. Shortest routes. C++ 20 and some. Let's see. And I have this one as well. Okay, I also have this one. I got this from college. That is pretty not nice. And 32-bit limit is in this. Yes, it is this, but I was saving here int max right shifted by once. So int max divided by 2. And how do you know the exact limits? This number divided by 2. We have 10737 something. And now this one is correct. This one is also correct, but way down the line something happens which is wrong. But in the earlier one, the wrong answer was this exactly 10737 something. Yeah, maybe for Alan Turing or someone like that, or someone like Mr. Neumann, Mr. Johann Neumann. And by the way, John von Neumann was able to multiply 8-digit numbers in his head when he was 7 years old. So he might have been him, might have been a little genius. Int max. Okay, shit. Can I use the global command to run the substitute command on every line wherever a pair appears? Wherever the word pair appears, only run the substitute command on those lines. But the command has to be normal. No, command can be anything. Global pair, and the command that needs to be run is substitute on these lines integer with long global. That was by the way crazy. Gamers have this in mind like 2 billions, 47 million. So shit, in words, they have this mind in words. That is crazy. So you are a gamer with the Kinesis Advantage Pro 360 completely wireless with brown switches. That is pretty nice. And did you saw what I did just now? Uh, no, shit. I messed up. How do we open the? Yes, this command. This command is amazing. Call the global command on all the lines which have the word pair, and call this command on all the lines which have the word pair. And this command is just calling the substitute every appearance of int with long globally, like on the whole line. That is crazy Vim thing. That is also cool. Used to be a gamer. Those days are gone in the past. Okay, shit. So range is not a error. Spot the error. I think this value is wrong. Wrong answer does not even make sense because this should work if the cycles do not have a negative weight here. And there are no cycles with a negative weight, so this should work. Let's read the implementation. Yeah, let's read the implementation and not waste time. The following implementation of Bellman-Ford algorithm determines the shortest distance from a node X to all nodes of the graph. Let's rewrite this because I want to get this right. N, M, C in N and M, and we will have a vector long path and vector of pairs and the node that the current node is connected to and the weight. And this is called ADJ. Cool. And after we have n, we can say p dot assign size n. Was that the error? No, that was not the error. We had n plus 1 error, so that was not the error. Pn plus 1 and the initial value. Let's make the initial value very big. What is the biggest value for a long positive value? Yes, I do use Git. Lazy Git, yes. No, I think lazy Git we can use Git in new vim without leaving new vim. No, I do not use that. I did saw that, but no, I do not use that. I saw that in a Primogen video, but no. Okay, I think the error is this initial value because sometimes the sum get bigger than int max. So we have to calibrate for that. Biggest value long C++. That is amazing prompting. Long max. But if we add something to this thing, this will become negative. So let's use this number divided by 2, and that should be good enough. Right? Yeah, that should be good enough. And now adj dot assign size n plus 1 for each node, and internally vector pair for int long. And let's take some risks and substitute long with integer because whenever we are adding this weight to something, we are only adding this weight to the path which is already long. So yeah, there shouldn't be any problem because of that. And with that, L R W less than N R plus C in L R W and ADJ L dot push back R with weight W. Shit, and this was directed. Why was didn't I saw that this thing is directed? Easier than get. C easy to commit. C to commit. P to push. No useless writing. Okay, I will see that. I will look that up. Lazy git. Wait, is this the thing? It's just the two. Stefan Haller from Germany, Deutschland. I think, yeah, this is not the, wait, this might be the thing. Is this the thing? This might be it. That is too much information. And we can also build our own Git from build your own X. P1 equals 0. And now we need our function BF, Bellman fold, int I, auto X W N ADJ I if P path to get to X is greater than P I plus W, then P X equals P I plus W and called BF Bellman fold on X. And after this, for int I equals 1, I less than equal to n I plus plus. And yes, I messed up again. This has to be M. C out, Pi, and depending on I, this or new line, I equals M. Has to work at least for this, or maybe not if we do not call the function BF for 1. Alright, cool. And does it, yeah, let's see. This has to work. Has to. Okay, that is the one. Lazy Git. Yes, that is much better than wrong answer. Time limit exceeded is much preferable than wrong answer, because we can get away with time limit exceeded if we go and read about Dijkstra's algorithm. And that is what we are going to do next. Let's read about the implementation and we will move on to Dijkstra's algorithm and we can consider Bellman-Ford done. Yeah, it is done. The following implementation of the Bellman-Ford algorithm determines the shortest path from a node X to all the nodes of the graph. The code assumes that the graph is stored as an edge list. As an edge list. Also, you are not doing BF because you are recursing to the next node as soon as you relax an edge. So this is DFS. So I should implement BFS. Shit. Exponential edge case. That does make sense. That does make sense. So what I'm doing is BFS. I should do something similar to what I'm doing is DFS. Taking one path and thinking that it is the best path there, and if I find some at some other point that there is some other better path, we go the whole way again, and that is bad. So something similar to BFS should be implemented, and if that is the case, and yes, here also they are saying thing is stored as a edge list. So we will read about this. Let me implement this as a BFS. And if we are going to go with BFS, if my understanding is correct, then we can like declare these things here. Size n+1 and vector pair int is enough. a size n plus 1 and vector pair in and that is cool. Cool. We don't need this. We can have a queue of integers. We will call it q and q dot push one while not q dot empty and I equals q dot pop q dot prop q dot pop and for int auto x w n edj I everything that is connected to I if path to get to x is greater than p pi plus w then px equals pi plus w and u dot push x. Okay, and I equals 1, I less than equal to n and I plus plus c out p I adjl dot push back something is wrong. Adj was not declared. Yes, makes sense. Q dot front doesn't work. It does. BFS won't change the runtime if you are still pushing distances in descending order of each edge. Hmm. Okay, I do get why DFS is bad, but like descending order in terms of distance. Okay, so here I am pushing everything onto the queue if the current distance is better than whatever the best distance till this point is. And that is bad because we are adding things. That does make sense. That does make sense. I can think, okay, like if we have things like this, let's say this goes on for a long time and like this, and we have something like this. And this is like a very big number, and this is 1 and this is 2. And in DFS, when we start, let's say we will go to this and we'll say the best way to get to this thing is 1000. Then we'll go to here, we will go to here. So BFS implementation, the earlier one was like obviously bad. But now this one, DFS was bad, like visibly bad. But this one with BFS is also bad. And I think I get your point. It is, let's say our first step, we go to here and here. The best way to get to here is 1 and the best way to get to here is 1000. And then we go to here, here, and here. And we see that the best way to get to this point is 3 now, and 3 is better. And we are already going here, going to go there. And in the next step, we'll go to this place with a distance of, assuming we started with a distance of 1000, and that is bad. We do not want to do that because the distance for this place is already updated and it is not 1000 anymore, it is 3. So we have two things going in the same direction. And this is even not worse in time complexity manner. We're saying won't change the runtime. And yes, I think, yes, we can make our argument. This will not change the runtime, but this looks even worse than the last one. At least the DFS one was making a little bit of sense, but here we have multiple things going in the same direction with different initial distances, and this looks stupid. So let's read the actual implementation. Edge list, the standard, and the best, the better way to do this. The code assumes that the graph is stored as an edge list, which was the third representation in CACS book. That consists of tuples of the form A, B, W, meaning there is an edge starting from node A to node B with weight W. Okay, the algorithm consists of n minus 1 rounds. Okay, so we will be done by n minus 1 rounds. N minus 1 rounds. N minus 1 rounds. So time complexity would be n minus 1 into the number of edges. Okay, and that is why this is slow. Yes, this seems to be still exponential and bad. And since they are saying in the implementation, this is going to go through all the edges n minus 1 times. So the total time complexity is going to be n into m, and that is bad. And that is why you said that Bellman food is bad and we should go with the Scratch algorithm. Okay, let's at least implement this thing once, and then we will move to the Scratch. Wait W. Okay, the algorithm consists of n minus 1 rounds. On each round, the algorithm goes through all the edges of the graphs and tries to reduce the distance. Okay. Okay, I think I can now implement this. Yes, we will fill not like this. N minus 1 pairs not push back, but instead, wait, auto reference um, LR W equals ADJ, and there are M edges, so M. And this, but pair, yes, yes, this cannot be a pair now. This has to be a tuple, and we can say using TP equals tuple of end, end. Initialize the tuple, and wait, this is not the right way to get things out of a tuple, right? We have to use the get syntax, get bracket something. See, in get 0 bracket ADJ, adj I. This does look stupid. 1 adj I and get 2 adj I. I already think this is like kind of broken. For int I equals 0, I less than n, because this has to go n minus 1 times. And why does it have to go n minus 1 times? Because that is the longest path. N minus 1 would be the longest path, and once you have gone through all the edges n minus 1 times, through all the edges n minus 1 times, then we are already like pretty cool. We can optimize this a bit. C chain equals false, and if we ever find an edge which does make a change, we will update change, but if no change, then break. And now we will go through the edges, and j equals 0, j less than m, or yes, that is the way that you will have to go. I don't think we can use the unbinding syntax on a tuple. J equals 0, j less than m, j plus plus. The number of edges in a path is number of nodes minus 1. So you basically simulate building a path for that length. So you could just use a vector instead of vector tuple, a vector of 3 elements. That does make sense. How to be consistent and code every day. Just be consistent and code every day. Every day there is no how. Uh, Getter methods for tuples are a bit annoying to write. Yes, they are. And how to be consistent? You just have to be consistent. Like, there is no trick. There is no trick. You just have to be consistent. Just show up and do whatever you decided you have to do. Decide something and do it. And yes, Jordan Peterson says, be humble enough to pick small tasks, like clean your room, and he would be a better person to understand this statement from. So yeah, should not use a tuple. Yeah, that does make sense. Wait, vector can, and this would have resulted in an error. Like, what the hell is this? Can I use this? Something like this? Nah, I think that would be bad. Vectoring. Vector integer of size cn, or we can now actually decouple the thing, unbind the thing, or auto LRW equals ADJI. Is this okay? Let's see. Start plan D. Okay, that does seem to be okay. That does seem to be okay. See, L, R, and W. Okay, that is not okay. Client type value, aka vector integer, decomposes into 6 elements, but only 3 were given. 6 elements. Why does it decompose into 6 elements? 6 things which describe the vector. Okay. Cn ADJI bracket 0 ADJI and j equals 0. J smaller than 3 j plus plus a b j I j. Much better. LSP stop. All right. This thing and this thing, and internally we will update, and that is 2. Yeah, that's it. Yes. I was doing that, but then I thought maybe at some point the number of things that we are taking in might increase. So as a good programmer, we should do this. But that also makes sense because the number of things that we are getting, that is the value of j, is not going to increase. And also this is not like the number of moves in a grid when we move, like up, down, right, left, which can increase to diagonal moves also. So it does make sense to store that thing in a separate data structure, but here we can manually type it. 1 ADJ I bool. Now, if P ADJ I J, the path to get to J is greater than the path to get to ADJ I J plus AD. Wait, what? Shit, shit. I messed up. Okay. For no. If ADJ path, yes, path to get to the starting point, and the starting point is ADJ J, which is the jth edge, and the starting point, the ending point in the jth edge is 1. If that is greater than the starting point, the best way to get to the starting point in the jth edge, the starting point is this, and plus ADJ from the jth edge, the weight for that edge. If that is the case, then we update the path, and I think it will be better to take these values outside int L, R, and W. L equals ADJ J1, J0, and R equals ADJ J1, and W equals ADJ J2. P to get to the right edge is greater than P to get to the left edge plus W. If that is the case, then R equals P to get to L plus W. Yes. And that is about it. And also, if this is true, change equals true. Should have worked. And yes, does this make sense? Came out of J. That is a nice joke. And if Eric, you are still here, does this make sense? Doing instead of taking long max, I'm taking long max divided by 2, because when we do plus here, this might mess things up, right? Because if this thing is long max and P is storing long videos, long values, and we add w to long overflow. So I think this thing should make sense, or there might be some better way to do this also. See out pi this or a new line I equals n. Okay, cool. Yeah, it is now at least working in a working condition. Let's see. Uh, Shortest route, submit. And how much time has it been? It's been 1 hour and 41 minutes. And we have not done a lot of things. Okay, time limit exceeded is fine. How many time limit exceeded were we getting before? Yes, before it was mm, this many time limits, and now it is much better than before. And yes, so that is improvement, and that is good. That is the most we can get from Bellman food. Shortest path from a fixed source. And this is the thing. We have things in a edge list representation. Okay. And n minus rounds, n minus 1 rounds, because that is the longest path that we can have in the whole graph. For I equals 1 to n I plus plus distance, we are putting in distance to be equal to infinity, and distance x, the starting node. Yeah, we are finding the distance from x from the starting node equals 0, and then we will go n minus 1 times, and auto edges, we are going through the edges. Tie. Huh, I've heard that. Tie. How does tie work? We have a tuple, mm, tuple, with C++ 17 and later structured bindings offer provide a more concise and preferable alternative for tuple unpacking. For tuple unpacking. So we can use a tuple here instead of this, and that would make sense. Auto L, R, and W equals ADJ J. And we will have to change things here. Make this a tuple of int, and this thing also. Tuple of int, and here you can use the same thing. Auto L, R, W equals ADJ I. Same L, R, W. Mm, yes, no, better. Yeah. So we can use this thing to unbind tuples, but before C++ 17, we had to use the tie function to unbind a tuple. I think we can still use that thing. L was okay, we have to declare these things beforehand. L, if we want to use the tie function. And how do we say a reference? We do not get a reference. Uh, okay, we do not have tie for a reference. So this is bad. Auto reference L R W. Cool. And implementation, the time complexity of the algorithm is big O of nm, which is very bad because the algorithm consists of n minus 1 rounds and iterates through all m edges during a round. If there are no negative cycles in the graph, all distances are final after n minus 1 rounds. Yes. Because each shortest path can contain at most n minus 1 edges. Makes sense. In practice, the final distance can usually be found faster than in n minus 1 rounds. Thus, a possible way to make the algorithm more efficient is to stop the algorithm if no distance can be reduced during a round, which we do here. Change false. If we do make a change true, but if change is false, after going through all the edges, we break. And that does make sense. I wonder how tourists or Chiang feel when they see a question. I think they just go with their guts at this point. They feel like, shit, one more easy problem. Yeah, that is how they must feel. So that is nice. Negative cycles. And Jiangli is like if you read code that is written by Jiangli, it is very simple. Uh, yeah, it is like very straightforward. Feels like he is writing in English. We can actually read a code. Let's see. And this is how he looks like in real life contests or submissions. He did a easy problem. A, be positive. Given an array A, shit, this is the division 3 problem that you were talking about. That is his wife, bro. He's a guy. Shit. Yes, he is a guy. That is his wife. Shit. Japanese wife for a Chinese person. Given an array A of n elements, where each element is equal to minus 1, 0, 1, and one operation, you can choose an index I and increase. Okay, every element is minus 1, 0, or 1. We can choose an index I and increase AI by 1. That is assign. This operation can be performed any number of times choosing any indices. The goal is to make the product of all the elements in the array strictly positive, the minimum number of operations. That is this. So we will see how many zeros there are and number of zeros, add that to the answer, and the number of minus ones, add that to the answer. That would be our answer. Here 1 0, and number of minus ones multiply by 2, add to the answer. So 2 plus 1 3 3, 4 plus 1 5. Shit, this does make sense. This does make sense. If minus 1 is odd, if the number of minus ones is odd, then add 2. And how many number of zeros are, you will always have to add 1 to the number of zeros. So 2 for this and 2 for a single one. Yeah, that does make sense. So number of zeros plus, take the last bit from the number of minus ones and multiply that by 2. And what is the rating of this problem? This is the easiest problem. Problem A, be positive. And let's see his solution for this. So he takes in the number, then he takes a simple normal static array of size 3 and he declares a inside the loop that he's running and a standard cn into a and a plus 1 plus plus. And if a is minus 1, then the zeroth thing will be increased by 1. If a is 1, if a is 0, then the value at index 1 will be increased. And if a is 1, then the value at index 2 will be increased. And that is amazing. And then answer equals the number of zeros we have plus take remainder of the number of minus ones we have and multiply that by 2 and return the answer. Standard out. His code is like you can read it and you will understand what he is doing once you are packaged instantly. For them, tech rounds must be like rapid fire questions only. Yes. Uh, yeah. Implement BFS. You have 10 seconds. And this thing that I do here, print out a space or a new line depending on what the value of I is. This I came to know from Mr. Jiangli's code, and that is pretty cool. And do you know if you have three variables, let's say, if you have three variables A, B, and C, and your target is to make them like this. A has to be the greatest, then B, and then C. Then what you can do is if A smaller than B, then swap A and B. So now A after this line is guaranteed to be bigger than B. And if A smaller than C, then swap A comma C. Now A is the biggest element and only B and C could be out of order. So if C greater than B, swap B comma C. And these three are now sorted and that is pretty cool. This I saw from once I was reading Tourist's code and this is just like little things that they use. Swapped my brain with him. You can maybe call that function with him. That is why I'm just rich. I'm just rich, not skilled. Shit. That is a flex, I guess. Okay, now getting back to the thing, the main thing, negative cycles. The Bellman-Ford algorithm can also be used to check if the graph contains a cycle with negative length. For example, the graph this contains a negative cycle, which is go to from 2, go to 4, then go to 3, then go to 2 again. That is a cycle. And also the cycle is negative because we have two positive numbers which add up to 3 and one negative number which makes the total thing minus 4. If the graph contains a negative cycle, we can shorten infinitely many times any path that contains the cycle by repeating the cycle again and again. Thus, the concept of a shortest path is not meaningful in this situation. That does make sense. A negative cycle can be detected using Bellman-Ford algorithm by running the algorithm for n rounds. If the last round reduces any distance, the graph contains a negative cycle. That makes sense. If there are changes even in the nth round, then there is a negative cycle. Note that this algorithm can be used to search for a negative cycle in the whole graph regardless of the starting point. That also makes sense. SPFA, the shortest path finding algorithm, faster algorithm, is a variant of the Bellman-Ford algorithm that is often more efficient than the original algorithm. The SPFA algorithm does not battery and yes, And that is nice, right? That does look pretty good. Who wrote Python and C? GH? Bro is writing Vim shortcuts, I guess. Hello. Hello. I did read your message. I think there is another message you just sent which I haven't read. Jharkhand. Also, if you want to check if two numbers A, B are both greater than or less than a third number, then instead of doing A greater than 0, B greater than 0, or A lower than 0 and B lower than 0, we can simply do, yes, that is true. That is true. Both of these things are true at the same time, and both of them are greater than 0. That is true. The algorithm maintains a queue of nodes that might be used for reducing the distances. Ah, the SPFA algorithm does not go through all the edges on each round, but instead it chooses the edges to be examined in a more intelligent way, unlike us. Okay. The algorithm maintains a queue of nodes that might be used for reducing the distances. First, the algorithm adds the starting node to queue. Okay, first the algorithm adds the starting node X to the queue. Okay. Okay, so there is a so this is like BFS. Then the algorithm always processes the first node in the queue. When an edge reduces the distance, node B is added to the queue. Shit, that is BFS. The efficiency of the SPFA algorithm depends on the structure of the graph. The algorithm is often efficient, but its worst case time complexity is still O of nm, and it is possible to create inputs that make the algorithm as slow as the original Bellman-Ford algorithm. Yes, this is just BFS. Makes sense. And now on to Dijkstra. And I think we can consider Bellman-Ford completed at this point, because we have gone through whatever little information we have. We have unconsciously implemented SPFA algorithm before even Bellman-Ford. We know about negative cycles. We have done the implementation. We do understand the theory, Bellman-Ford, and that this does not work with negative cycles, and this is not very fast. The time complexity is the number of edges multiplied by the number of nodes, and that is slow. Now, this graph, which is much better, and there is also CLRS, but we will not go to CLRS for this, not on stream at least. And minimum spanning tree, single source, Bellman-Ford, describes the algorithm, Floyd, Warshall. Shit, this seems to be like shorter. Anyways, Dijkstra. How do you even pronounce this? Edgar Dijkstra. He has lectures on YouTube, which is crazy. Edgar, Edsger, Edsger Dijkstra. And he does say something to programmers.
One final request to one final request
A request.
to you. Having seen how we can convince ourselves that programs indeed are totally correct,
Mhm.
please realize that if you have written a program and it's not correct, that is a little bit cowardly to say that your program had a bug.
Uh-huh.
To call errors, bugs, is a very primitive, animistic attitude, suggests that the bug has a life of itself and that you're not totally responsible for it. That the mean little bug crept in behind your back at the moment you were not looking. Yeah? Well, this is not true. If the program is not correct, you made an error.
Yes.
And my request, my prayer, so to speak, is that you stop using the term bugs for program errors, but call them what they are, errors. Unless we change our language and call an error, programming and computing science have not yet matured.
And I think we can totally agree with the guy. If there is a like mistake, if your program does not work, it is because you made a mistake, not because a bug crept behind your back into the program. That is a right attitude, not just towards programming, but towards life. Discra's algorithm finds the shortest paths from the starting node to all the nodes on the graph like Billman food. The benefit of Discra's algorithm is that it is more efficient and can be used for processing large graphs. However, the algorithm requires that there are no negative weights in the graph. There are no negative weights at all in the graphs. Okay. Like the Billman food algorithm, Discra's algorithm maintains distances to the nodes and reduces them during the search. Discra's algorithm is efficient because it only processes each edge in the graph once, using the fact that there are no negative edges. Okay, we process each edge only once. That is beautiful. Let us consider how this class algorithm works in the following graph when the starting node is 1. This is the starting node, and let me turn off the fan. 1 minute. And now we are at this class algorithm. Like in the balloon fold, let us consider how Discra's algorithm works in the following graph when the starting node is 1. Right? Like in the Bellman fold algorithm, initially the distance to the starting node is 0 and the distance to all other nodes is infinite. Okay, initially distance to the starting node is 0 and to all other nodes it is infinite. At each step, Discra's algorithm selects a node that has not been processed. Okay, select a node that has not been processed yet and whose distance is as small as possible. The first such node is 1 with distance 0. Okay, okay. E. Etzker, W. Etzker published the algorithm in 1959. However, his original paper does not mention how to implement the algorithm efficiently. Okay. When a node is selected, the algorithm goes through all the edges that start at the node and reduces the distances using them. Okay, so we have gone through this edge, and this edge. Now, these are the possible nodes we could use. And among these, 5 has the smallest distance. So we will go through all the edges which start from 5 and update the nodes which are connected to 5. But we won't go through this one, right? Yes. How do we make sure that we do not go through this one? This edge, which has a 1. I guess we can, no, we cannot say that one is visited because fourth node is also visited, so we won't go there either. We can see, no, I guess we would have to consider this edge also. So every edge would be considered twice. And when we are at this edge, we will see the distance. We'll make the distance minimum to whatever it is, but the distance here already is minimum, so yeah, won't have any effect here. And here it would, this thing from 5, the distance would reduce from 9 to 7. And then we would have this edge as the shortest. In this case, the edges from node 1 reduced the distance of nodes 2, 4, and 5, whose distances are now 5, 9, and 1. In this case, the edges from node 1 reduce the distances of nodes 2, 4, and 5, whose distances are now 5, 9, and 1. Makes sense? The next node to be processed is node 5, which has a distance of 1. This reduces the distance to node 4. So we will have a priority queue. Yes, we will have a priority which will be storing pairs where the first number is the distance and the second number is the node. This reduces the distance from 9 to 3. Yes, and now the shortest is from 3. After this, the next node is 4, which reduces the distance to node 3 to 9. A remarkable property in this Kranz algorithm is whenever a node is selected, its distance is final. For example, at this point, if point of the algorithm, the distances 0, 1, 3, and 3 are the final distances to nodes 1, 5, and 4. After this, the algorithm processes the 2 remaining nodes and the final distances are as follows. That is amazing. That is like actually pretty cool. The efficiency of Dijkstra's algorithm is based on the fact that the graph does not contain negative edges. If there is a negative edge, the algorithm may give incorrect results. As an example, consider this graph. Okay, so we start from 1, which has a distance of 0. Then we, yeah, then we update distance of 2 to be 2 and the distance of 3 to be 6. Then 2 is the shortest thing and we update the distance of 4 to be 5, right? And now 4 is the shortest path, which has a distance of 5, 2, and 3. But that is a mistake. It would have been better to go here and then go here, and the distance would have been 1. That makes sense. The shortest distance from 1 to 4 is 1, 3, 4, and the length is 1. However, the Dijkstra's algorithm finds path 1, 2, 4. 1, 2, 4. By following the minimum weight edges, the algorithm does not take into account that on the other path, the weight 5 minus 5 compensates the previous large weight 6. Okay, we will not read the implementation. We will do the implementation. Yes, Dijkstra's. Let's go. And I just played a video about Mr. Edsger Dijkstra. Edsger Dijkstra. Edsger Ger. Name is just amazing, and he is Dutch. Who is another Dutch famous person? I think Max Verstappen. Yeah, he is also Dutch. Max Verstappen. Max Verstappen. Yeah, he is Dutch. Dijkstra. And now we will implement Dijkstra because we do understand the theory, we do not understand the implementation. And how are we going to store the data? First of all, Since what do we need when we are at a edge? When we are at a node, we need all the edges that go out from that node. So we will be using adjacency list representation. That is nice. That is not bad. Int n m c n n m c n n. And yes, I don't think we will need to call a function. We can have our priority queue run dry. Yes. Vector long p, which will have n plus 1 things, and long maths right shifted by 1, and vector pair in adj size n plus 1 vector pair in yes. Cool. I have a question. How many questions do you solve in a day? Because I have just started DSA and can barely solve 2 questions in a day. And sometimes I see the solution. Is it a bad habit? No, looking at the solution is not bad. Look at this. You have two options. Either you look at the solution, but before looking at the solution, you have to make sure that you will be unable to think of a solution on your own. Yeah, if you are unable to think of a solution on your own, only then look at the solution, because let's say you get this problem, find the shortest route. Are you going to sit down and invent Dijkstra's algorithm by yourself? No. You look at the solution, you read the solution, and you implement it. And when you have looked at the solution, you have to make sure that you can re-implement it again and again, and that you do understand the question. So yeah, just keep in mind that you do not have to invent new things. That is good enough. In N, R, and how many questions I solve in a day? That was another part of the question. Uh, I would say it depends. When right now I'm not solving a lot of questions because I'm reading theory, but when I do CP31 sheet streams, in those times I'm solving more questions than I'm solving right now. So yeah, it depends. It is not a fixed number. And after this, A D J L dot push back R dot W, this edge, and that is cool. What do we need then? We need a priority queue of pairs of integer of long integer long, and we will call it q, and q dot push. Yes. Nope. 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 Long in. The weight has to come first, and then q. But essentially we are uh, storing the same thing twice in a sense. Long is also here and also in P, but that is fine. That is fine. We that is fine. Yes. Yeah, that is fine. Q dot insert distance 0, 1. And the question is, does the priority queue by default return the elements, the smallest element first or the biggest element first? TQ C++ min heap. We want the minimum element first. We have to apply, give this function greater. Okay, cool. We can do that, we can do that, we can do that. Vector of pair of integers and greater pair of integers. I think that should be good. LSB start clang D. Okay, something is wrong. Indemnate static failed to requirement is same. Makes sense. Yes. Right. Okay, we can do substitute. We can do substitute on this line. Whenever we see a this and then an integer, replace that with this and a long globally, and the error should have gone. Let's restart, and the error is actually push. Let's restart, and yes, the error is gone. While not q dot empty, while q is not empty, we will get the shortest distance and also the node. The distance we already have. Thanks, bro. I was really regretting it. Okay. Yes, regret. Either you waste time, waste is not the right word, but you either you spend time regretting what you did yesterday or like an hour ago, or you like actually work hard right now and make it better. So yeah, do not regret anything that you have done. Make it better. X is the node equals this, and we will get q dot front or top I think is the word, top dot pop of the thing, and I is the node which has the shortest distance, and now we will go auto x w. Yes, xw adj I, every node x that is connected to every node x that is connected to the node y with weight w, and we will update this thing, and if we do update we will uh, add this to the queue. If the current distance, which is px, is greater than pi plus w, then we do first of all px equals pi plus w, and then we do q dot push weight is new px and x. For int I equals 1 I less than equal to n I plus plus C out. Yes, use curly braces. C out, we output pi space or a new line depending on I equals n. Hopefully this works. And this does work. And hopefully this is also faster. Real fast. I'm speed fast. C++ 20. Yes, let's see. Dijkstra's algorithm and That is messed up. We have queue. I think we are not adding anything to the queue, and the implementation is messed up. Look at this. What is this? Priority queue. The thing with the smallest weight is node 1. I is that node. We don't need the distance because we already have the distance from here. And for auto x, y, x is the node that the ith node is connected to, and w is the weight. This should be true. Shit. That was a mistake. And this is not the first time that I've made that mistake. Shit. We are not taking all the edges. So, what tools are you using to check the test cases? In NewVim, there is a plugin we can use. It is called Assistant in NewVim. Let me just check this if this is correct. Okay, that is very good. That is very good. We just have to optimize. At least we are doing correct. There is this plugin in Assistant NewVim which we can use for checking test cases. This thing that comes up, this window, this is because of this plugin, Assistant in NewVim, and this is a very good plugin. But when I want to give custom inputs, there is a binding which this guy, not AYY clips, he gave, and his binding is pretty cool. I do not want to admit, but his binding is pretty cool. We can just run a function now. Here on the right side, I can give any input that I want. Let's actually grab some input. Copy, paste, and we do get the answer. So that is cool. That is very cool. Yeah. And the binding he gave is like pretty cool. Okay, so the thing is not optimized, it seems. But for what? Empty. Because time limit exceeded makes sense. There's this test case where we got wrong answer. Is there something that we can optimize? So Q all only has the nodes which have not been visited, right? Yes, kind of. At times, this might have some nodes which we don't need. Shit, yes. This might be bad. Yes, yes, yes. So can we have a map of all the things? Can we do we if I think if we store a map where the key is going to be the value, where the key is going to be the weight, minimum weight of the path to get to that point, then it is good. And the value is going to be an array. Yeah, and we can go to any of those nodes in the array using with that much weight. And that is good because we have the ability to update the weights. And if the size of an array becomes 0, we just delete that thing. I think that might be good. I mean, we will look at the implementation in a while, but let's try to optimize this on our own. So we will not use a queue. Instead, we use a map. A map. Okay, LSP is on. Stop the LSP. E is going to be long, the weight, and integer value. MP map. MP bracket 0 equals 1. Shit. This thing has to be a vector of integers. And would we have to create vectors? Push backward while MP dot type. So yes, and let's get integer I equals MP dot begin the smallest value. Go to MP dot begin by doing this thing, and there we are going to get the second thing, which is the second and second 0. Shit. This is like too many layers of things. IT equals MP dot begin, and then int I equals go to IT and dot second, which is our vector, get the first value from that vector. And at this point, we just want, but shit, how do we update when I have a node? How do I know what is the weight that the node has? We can look up the weight because we do have the original weight in pi and the p vector. We can look it up there, but when we index into the map using that particular pi weight, px weight, it is going, we will get a vector. And a vector, no, we do not want to look up in a vector for the node that we are looking for. So yeah, set. Maybe you could have a set instead of this, instead of a vector, and that would actually be fine. Yes, let's just go bonkers with this. We can look up the correct implementation later, but right now let's do this. Insert 1, get map second shared. Since now this thing is a set, we have to go to its iterator, like by using dot begin and get the value there, and then we will pop that thing. Shit, there are just a lot of iterators here now. C, we will call this S as in set, and int I equals S is a set, but we are getting its begin thing. Wait, do we use the brackets here or don't we? I don't know. So IT go to S, get the value at this place, and then remove this value from the set, for which we have to uh, go to IT dot second, which is a set, and in this set dot erase S. And now when we have erased S, we need to know the size of this set. And if the size is 0, we delete this value. We delete this key. If that is just too many layers, go to IT dot second, which does return a set. And in this set, dot size, get the size of the set. If this size is like 0, if not size, then how do we delete a key from a map? mp dot erase it, I think would work. mp dot erase it, yes. I think it should work. Yes. LSP start. Okay. LSP start client D, and there are errors. And why is the error have a line here? Which this line looks like pretty cool. Yeah. So we do not use these brackets. That makes sense. LSP start and LSP restart. LSP restart. Cool. Okay. Now we can process S. We can process I. This is very bad, but okay. This might actually be faster than the other one, than the previous method. Previous. ADJI. Every node that is connected to I. And if no, no, this is bad. No, we will not do this. We will not do this. This is like obviously very bad. No, there's just a lot of overhead just to maintain the invariances. Like, look at this much code, not this much code to just get. We are writing this much code to just get the node with the smallest distance, and this is not good. So yes, let's look at the implementation, the correct implementation. The following implementation of the Scruz algorithm calculates the minimum distances from node X to other nodes of the graph. The graph is stored as a adjacency list, so at least you got that much correct. So that ADJI contains a pair BW. That is also exactly what we did. Always when there is an edge from node A to B with weight W. An efficient implementation of Discruz algorithm requires that it is possible to efficiently find the minimum distance node that has not been processed. Yes. This is the thing that we were struggling with. An appropriate data structure for this is a priority queue that contains the nodes ordered by their distances. But how do we like change the values inside a priority queue? Using a priority queue, the next node to be processed can be retrieved in logarithmic time. In the following code, the priority queue contains pairs of the form distance is negative and x. Okay, negative distance so that we can make do with a max heap, right? Whenever a distance is larger, it's like, yeah, whenever a distance is smaller in absolute terms, its value is going to be higher than a distance which is larger in absolute terms. And since our priority queue is a max heap, we will get the smaller distance. That makes sense. Instead of what we were doing. We were using passing in functions so that we do have a mini heap, but this is better. This is better, meaning that the current distance to node X is D. Mhm. The array distance contains the distances to each node, and the array processed indicates whether a node, okay, and if it has been processed, then we do not process the node. That makes more sense. Let's write that, and n m and LSP stop. We do not use LSPs. Okay, and now after taking in n and m, we describe our data structure adj size n plus 1 vector pair in yeah, initialize, and vector long p size n plus 1, and initially all the values are long max divided by 1, and vector visited size n plus 1 and false initially. We could use a bit set. This is also fine, and this is going to work. Plus plus, and in L, R, and W, we will get seen L, R, and W, and here then ADJ L. We have a node going from L, push back to R with the weight W. Sorry, we have a edge, not a node, which does this, and then we will need a priority queue, and we will also say path to get to 1 is 0, and we will push this into our priority queue. Priority queue, which is storing pairs of long integers. We'll call it queue, and queue dot push distance 0 1, while queue, while not queue dot empty. And also we will say that this has been visited. So instead 1 equals 2, we will get the top node, and yes, we will get the top node, and this is a pair, so we can just use auto. We don't need the weight, we just need the index of the node, equals q dot top, and then q dot pop, remove it, and if not visited I, then we process. And what do we process? We do for int, for not int, auto xw nadji, for every node that is connected to this ith node, for every node x that is connected to the ith node with a edge which has a weight w. What we will do is we will update the distances. Yeah, if p x is greater than p I plus w, that is the current path to get to x is greater than the path we could take if we go through I. Then we first of all we will update px equals pi plus w, and second of all we will push this into the q dot push distance is negative px, and the node is x, and also this has to be visited x equals. Or yes, we are only adding things which have not been visited. Yeah, we could say that we are only adding things which have not been visited. So if not visited X, only then do we check these things. Only then do we maybe try to update distance for X. And then we output for int I equals 1, I less than equal to n, I plus plus, C, P, I, space, new line, I equals n. Should have worked. There is a little typo at some point. If G, this has to be T, and how are other things? Pair, Q, pair, long, int. See somehow, yes. Okay, wrong answer is bad. Let me go to the washroom and I will be right back and we will fix this, whatever the bug is, and I'll be right back in a minute. You. I am totally back. And there is something wrong with this. We are not outputting the correct value. If not visited X, then check, are we reducing the distance by going to X? And if we are, then reduce the distance to go to X. And shit, X is of course not visited. If X, yes, there is a like obvious mistake. Okay, X is not yet visited. It is going to be visited. Yes. X is going to be visited. X is going to be visited. So in this thing, initially we just have one, and then we update the distance for this, and this, but we do not put them as visited. Yes, we haven't visited them yet. Yes, we haven't visited these nodes yet. Makes sense. So we do not do visited here, we do visited here when we are like actually visiting the thing. Hmm. Hmm. That does work. Cool. Let's submit this and see if it works. We were getting 3 wrong answers. Let's see if this screw works. Don't tell me this is reflex action. Same mistake again and again and again. And then one more time. Shit. Okay, let's grab a test case. And this seems to be correct. 911, the end thing is 27, 29. Yes. Okay, so that is correct. And there are a lot of things open. We can clean this a bit. Yes. Okay. So now we should be correct. Yeah, it has been a while. Okay, shit. These 3 things are still giving time limit exceeded. Let's see the actual implementation. Implementation of Discra an efficient implementation of Discra's algorithm requires that it is possible to efficiently find the minimum distance node that has not yet been processed. An appropriate data structure for this is a priority queue that contains the nodes. Are we making a mistake here? Priority queue. I think after getting I, if it was already visited, if visited I, then continue. Yeah, because we will have multiple occurrences of the same thing. So this should work. This should at least be better than the other one. Okay. Yes. Yes. Shit. Okay. Now, at least on the this normal test case, it does work. And yes, shit, this is bad. I should not be like submitting again and again. This is bad. This is not. That is a beautiful sight. That is a beautiful sight. And there is no one to watch this site with me, and that is fine. This is a beautiful site. Everything is accepted. That is nice. Let's one shot this now. Mm. I will remove the whole code parts and write again from scratch. And when we submit this, this has to be correct in the first try. So we get the number of nodes and the number of edges, and then we create paths. A vector which is going to store the paths in a long format. Size is going to be n+1. And initially, every value is going to be long max divided by 1. And we will also have a adjacency list representation which stores internally pairs adj size n+1 vector pair int, yes, initialize, and also a visited array, visited, not like this, vector bool visited size n plus 1, and initially everything is false, and then we will take in all the edges L, R, and their weight W, also I equals 0, I less than N, I plus plus, and C in L, C in R, C in W. Take the left edge, right edge, and weight for these things, and then ADJ L, we have a edge going from L to R, and the weight is W for these things. And then we will initialize our answer path to get to 0 is 1. To node number 1 is 0, and we will have a priority queue storing a pair, long pair, yes, and we'll call it q dot push. We will push onto our queue the values, distance is 0 and 1, and then we will keep running our loop while there is something in queue. While not empty, we will keep running, and auto, we don't need the weight, we only need the ith node from the top of the queue, which is queue dot top, and then we will also pop this thing off. After popping, if we have visited this thing before, visited I, if we have visited I before, then we will continue to the next iteration of this while loop. But else, if it has not been visited, then you will go through all the nodes X which have been connected to I with a weight W, ADJ I. And if not visited, X, if X hasn't been visited, then we will check if X, first of all, hasn't been visited, and second of all, Px, the price or weight to get to X is greater than if we were to first go to Pi plus W. That would be the weight. If that is the case, then what we will do is, and also if it hasn't been visited, we will say I is visited. And if this is the case, then first of all, we will update the distance Px equals Pi plus W, and then Q dot push weight is Px negative minus Px, and this node is X. Yes, if not visited and Px is greater than Pi plus W, then we go into the loop and we update the distance, and also we do Q dot push. Yeah, we push this into Q. We might want to go to this place at some point, and it might be the case that the current edge that the current node that we are trying to process has already been visited. Yep, and in that case, we will continue. Yes, because we might be adding the same edge multiple times into the queue, and if we have already visited that edge and we only visit a edge after we have taken it off of the queue at least once, and if we have done that, only then do we put visited I equals true, and also this thing. And initially everything visited is false, so that is also nice. And after that, we should have the answer for int I, and I equals 1, I less than equal to n, I plus plus. C out, P, I, this new line, I equals n. Yo, okay, that is the only mistake it seems. ADJ, where am I using a JD? JD vans, okay, right there. a DJ adjacent. That does work. And I want to one shot this. Like literally, this has to be correct the first time that we submit this. So is this correct? First, we are taking in n and m. N is the number of nodes and m is the number of edges. And then we are initializing three data structures. This data structure will say true if the ith node visited I has been visited before. And this data structure will have pi will correspond to the shortest path to get to the node I. And adj adjacent, if this is simply a adjacency list where adj I will have two things. ADGI is a list. It is a vector of pairs. And in that pair, the first number is the other node that this ith node is connected to. And the second number is the weight of the edge which is connecting these two nodes. So yeah, that is cool. And pair only stores integers. That is also true. And then we are this has to be m because the number of nodes that we have is m, not n. So we go through and we take all the nodes in, and here we are saying the left node, there is an edge which goes from the left node to the right node, and that edge has a weight w. Then we say that the best way to get to node number 1 is 0. The distance is 0. Then we initialize our priority queue and we put onto our priority queue that this is the distance. The first part in a priority queue is going to represent the distance, and the second part is going to represent the node which has that value. And that is nice. The node which has that value, yeah, that distance. And while the queue is not empty, what we do is we get the node which has the shortest distance currently to get to, and we see have we visited this node before. If we have visited this node before, we go to the next iteration of this while loop. But if we haven't, then we will say, now we are visiting this node, visited I equals 2. And then we will go through all the nodes that this I node is connected to. And W is the weight of the edge which is connecting the I node with the X node. And here we are checking if this X node to which we can go to from this I node, which we currently are at, if that X node has not been visited and the distance to get to that X node, whatever the current distance is, if it is greater than the distance it would take for us to get to the ith node and then go to the X node from the ith node. If that is the case, then we update the distance to get to node X, and we also put this thing in the queue with the updated distance, and the distance is negative because the priority queue is max heap by default and gives us the maximum number. So we are just reversing the behavior by putting a negative sign before that. And when queue is empty at some point in the future, then we are just outputting the distance, and this should work. Submit. And one shot, this has to like be one shotted, and it's been about 3 hours. We will now do. Okay, that is a very beautiful site. After a little bit of struggle, this is a beautiful site. Hey, cool. Dijkstra's algorithm, and yes, that is Dijkstra's algorithm. Implementation, this is the implementation. In the following code, the priority queue contains pairs of form -t and x, meaning that the current distance to the node x is d. The array distance contains the distance to each node, and array processed indicates whether a node has been processed. Initially, the distance is 0 to x, and infinity to all other nodes. Yes. So yes, here we are just initializing the distance, and then we are saying distance to the starting node is 0, and we push that node onto the queue. Now, while queue is not empty, we get the top thing. Ah, shit, that is something also we can do instead of doing this thing. And I equals queue dot top dot second and queue dot pop. Remove the thing. And then if processed A, then continue. That is exactly what we do. And then if not, then we are processing it right now. Then auto B equals first and W equals second. Yes. If distance W is smaller than the current distance to get to B, then put distance this and put this on to the Q, and that is cool. That is cool. Now we can move on to the Freud-Warshall algorithm. That would be nice. And we will be able to solve the next question about graphs on CACS. Yes, shortest distance first. Then we will also do shortest distance second, and it would be pretty cool. Okay. Note that the priority queue contains negative distance to nodes. The reason for this is that the default version of C++ priority queue finds maximum elements while we want to find the minimum element. By using negative distances, we can directly use the default priority queue. Also, note that there may be several instances of the same node in the priority queue. However, only the instance with the minimal distance will be processed. Yes, the time complexity of the above implementation is n plus m into log m. Why n? Because we are processing each node at least once, and but we are processing edges multiple times, right? Yeah, because the algorithm goes through all the nodes of the graphs and adds for each edge at most one distance to the priority queue, and log m to like find the best edge currently. And now Floyd-Warshall, that is I guess supposedly the big boss implementation, and that is it. Okay, there are two footnotes. Of course, we could also declare the priority queue as in chapter 4.5 and use positive distances, but the implementation would be a bit longer. The algorithm is named after R.W. Floyd and S. Warshall, who published it independently in 1962. 1962, what happened in 1962? I think Quentin Tarantino was born in 1962. Okay. I don't know the name of shit. Off by 1 year. My bad. Shit. I should have known that. Initially the distance okay. Okay, now on to Floyd Warshall, and that would be the last algorithm for today, and it will be pretty cool. The Floyd-Warshall algorithm, Floyd-Warshall algorithm provides an alternative way to approach the problem for finding the shortest paths. Unlike the other algorithms of this chapter, it finds all the shortest paths between the nodes in a single run. Okay, that is cool. The algorithm maintains a two-dimensional array that contains distances between nodes. First, distances are calculated only using direct edge, and after this, the algorithm reduces distances by using intermediate nodes in the path. Okay, the algorithm maintains a two-dimensional array that contains distances between nodes. Okay. Let's say the array is called ARR, then ARR ij would have the shortest distance from node I to j. First, distances are calculated only using direct edges between the nodes, and if two nodes are not connected directly, then the distance is going to be infinite, I guess. After this, the algorithm reduces the distance step by step using intermediate nodes in the path. Example, Let us consider how Floyd-Warshall algorithm works in the following graph. This one, all right. And initially the distance from each node to itself is 0, which are these values at the diagonal. And the distance between nodes A and B is x if there is an edge between node A and B with x weight. And by between, is it directed? And the question, how is the question? This is not directed because these are roads. Your task is to process Q queries where you have to determine the length of the shortest route between two given cities. Input the first input line has three integers n, m, and q, the number of cities, roads, and queries. Then there are m lines describing the roads. Each line has three integers a and b. A and b, there is a road between A and B whose length is C. All roads are two-way roads. Yes, two-way roads. Finally, there are Q lines describing the queries. Each line has two integers A and B to determine the length of the shortest route between the city A and B. And if there is no route, then output -1. Like in this case, there is no route between city 1 and 4. Okay, so initially the graph array is like this. Okay, this does make sense. Does make sense. Now, once we have gone through direct connections between nodes, we will do something crazy, I guess. We will process the intermediate presence of nodes. Okay. The algorithm consists of consecutive rounds. Okay. On each round, the algorithm selects a new node that can act as an intermediate node in path on from now on, and the distances are reduced using this node. On the first round, node 1 is the new intermediate node. Okay, so the algorithm consists of consecutive rounds. On each round, the algorithm selects a new node, not an edge, but a node that can act as an intermediate node in paths from now on, and distances are reduced using this node. Okay, so we will, but if there are, let's say, n m edges connected to node I, then we will have to pair up every single edge with every other edge. Time complexity n is square in that case, but that would be the case if everything is connected to just this singular node. There is also a new path between two. Okay, on the first round, node 1 is the new intermediate node. There is a new path between nodes 2 and 4. Okay, so this one is acting as a intermediate node now. And these fourth nodes are connected to node 1. So initially there is no distance, the distance from 2 to 4 is infinite, and that is bad. Instead of infinite, we can use go through 1, and the distance for 2 to 4 is going to be 14. That is nice. And then there is initially, yeah, we will also update path from 2 to 5, and that is it. So 2 to 4 and 2 to 5, these two things are updated. 2 to 4 with a length of 14, node 1 connects them. There is also a new path between nodes 2 and 5 with length 6. Okay, on the second round, node 2 is the new intermediate node. This creates new paths. Now node 2 is acting as intermediate nodes, and there are only two nodes which are connected to node 2, which are 1 and 3, and 2 creates a path between 1 and 3. That is nice. And then the next intermediate node is 3, and this connects 2 and 4. Initially, the distance between 2 and 4 was 14 through node 1, but now it is 9 through node 3. That is nice. And then we make node 4 as our intermediate node, and 3 things are connected to node 4, right? There is already the best distance between 1 and 5, so we do not bother with that, but we create a new distance, a new way to get from 3 to 5, which has a path length of 2, and yeah, that is it. The already distance for 1 and 3 is already there, so that is fine. And then for 5, yeah, it is better to get to make the distance between 1 and 4 through 5, because it is 3 instead of going there directly. On round 3 node 3 is the new intermediate node. There is no new path between 2 and 4. The algorithm continues like this until all nodes have been appointed intermediate nodes. After this, the algorithm has finished. The array contains the minimum distances between any two nodes. For example, the array tells us that the shortest distance between node 2 and 4 is 8, but that does not make a lot of sense. The corresponding path is this. Okay, so how are we deciding the intermediate path? The time complexity would be n cube if what I am thinking is correct. So for 1, we have 5 and 9, 2 and 4, and we see 2 and 4 are connected by infinity. So we make this thing 14 and we make this thing 14. Then for 2, we have 5, 2, 14, and 6. So 5 is 1 and 3. 1 and 3 are connected with infinity, so we update that and make that 7. And we have 1 and 4. Time complexity is kind of n square, n cube actually. It's like you, yes, it is actually n cube. So n is not very big. Okay, I think we can implement this without looking at the implementation. And we will one shot this. We will get this right in like the first try. And we will have a adjacency list. Do we need a adjacency list? I don't think we do. Vector, vector, long, long. Yeah, this is not a adjacency list. And yes, even though we are calling it ADJ, size n plus 1, and this is the answer list, answer matrix n plus 1. We have a matrix of size n plus 1 by n plus 1. And initially every value is equal to 0, but we have to change that, and we can do that by saying long max, right click by 1, and for int I equals 0, I int I equals 1. Yes, and I less than equal to n, I plus plus, a dj, I, I equals 0. Yes, and yes. And do we need to initialize any other thing? No. Int L, R, W for int I equals 0, I less than M, not N, and I plus plus. C in L, R, and W. And we will say ADJ L to R is W, and ADJ R to L is also W. And that is better stated with ADJ R L equals ADJ L R W. Okay, cool. Now we will keep making passes for int I equals 1, I less than equal to n, I plus plus. So now we are treating node 1 as an intermediate node, and what we will do is for int j or int L equals 1, int L equals 1, and L lower lower than equal to n, and L plus plus. And also n R equals 1, or L plus 1, L smaller than R smaller than equal to n, R plus plus. Smaller than n. Yes. No, we will not go to n. Yeah, we'll not go to n. And if we ever have L equals I, then continue here. So L is fixed. And if we ever have R equals I, continue, or we have ADJ L R equals 0. That is not. That would mean, or we this. Yeah. If L R is 0, I R is 0, then yeah, do this and check the same condition here. Or A D J I L is like 0, because that oh, shit. Okay, we are already checking the thing. This would only be true, like ADJ I J would only be true if I equals J, so we don't have to check this like multiple times. True. Now ADJ I R. So if we long new distance is going to be ADJ since I is acting as a intermediate node, we can say I to R plus ADJ I to L. That is the new distance. And we will say ADJ L R equal minimum, whatever its current value is, ADJ L R comma D, and do the same thing on the opposite side. R L equals AD, ADJ R L equals the same thing. And now we should be able to answer, but we are getting the something else here. We also are getting Q. Yeah, so we have to change the way that we are taking input, while Q minus minus and L comma R, wait, have, yeah, they are already declared, C in L and R. What is the best way to get from L to R? It is ADJ L to R and a new line. Out of bounds. What are we indexing that is out of bounds? N plus 1, N plus 1. Yes, true. X. Okay, the wrong answer is much better than the other thing. Okay, that is very good. We have to have a conditional here. See out depending on the value of ADJLR. If this thing is long max, right, so by 1. If this is true, then output minus 1, else output ADJLR. With a new line. Hmm. That does work. That does work. That does work. Floyd Warshall has been conquered. Floyd Warshall has been conquered, and that is very nice. And it has been 3 hours and 24 minutes. That is pretty nice. And we have made a lot of progress. We have done Floyd Warshall. We did all the 3 shortest path algorithms. But we have to first like submit this one. And before submitting, just make sure that we get this N and U, C in N, M, and Q. Then we would need our data structure, our amazing data structure. ADJ is what they call it, N plus 1 vector long. It has N plus 1 values, and by default they are long max divided by 1. And for int I equals 0, I less than M, not N, and I plus plus, we will need those values L, R, W, C in L, R, and W, and ADJ L R equals ADJ R L, which is equal to W. And also we have to initialize these things. I equals 1, I less than equals to N I plus plus ADJ, ADJ, L, ADJ I equals 0. We don't actually have to do this because we will skip this part. Whenever we do see, then we are indexing II. Now, is the array initialized? It seems to be. It seems to be. Okay, now we will go through all the nodes, and I equals 1, I less than or equal to n, I plus plus, and for int L equals 1, L lower than n and L plus plus. And if L equals I, then continue, else for, we'll run a for loop, R equals L plus 1, L R smaller than equal to n, and R plus plus. We'll go to the next one, and we have the current distance D would be equal to ADJ, since I is acting as a intermediate node, so distance from between I and L plus ADJ L R I R, that is the new distance, and we will update distances L R ADJ R L to be equal to the minimum of whatever the current distance is, ADJ L R common. And when that has been updated, we will run the query while q minus minus taken L and R, they have been defined above. See out depending on ADJ L R. If ADJ L R equals long max right shifted by 1, if that is the case, then output minus 1. Otherwise, output whatever the value is, ADJ L R with a new line, and this should work. This should work. It does work, and we are going to one shot this thing. We will just submit this and hope, not hope, and this should work. This should actually work. This should be correct. Let's see. This should be correct. Should be correct. Shortest route, part 2. Okay. Okay. Wrong answer. Wrong answer. Wrong answer. Okay. I did not expect that. Answer is wrong at times. I think this should be good enough if that was the mistake, and we'll do the same thing here. Minimum. We are taking the minimum. LRW. Long D equals this new distance. Since I is at FR equals I, then like continue shared. That was an obvious mistake, and we can also change this back to 10, back to 18. If L equals R, if L equals R, if L equals I, then continue, or if R equals I, then also continue. Okay, the new distance, it is I, L. Yes, since I is acting as a intermediate node between these two, then we will see and update the distances between L and R to be ADJ LR equal to D. Okay, okay, this should work now. At least this should work. Okay. It is also taking more time. So let's literally look at the test case. Okay, correct answer is 1, but why are there multiple paths between the same? Okay, that is something that I didn't know. So, so we have to change this. And if we are going to change this, we will have to long W, minimum of W, or whatever their current distance is. Okay, there are multiple routes between the same uh, cities. Now it should work. Okay, minimum W and ADJ LR. So this is at least not a simple graph because there are multiple roads between the same nodes, multiple edges between the same nodes, and are there loops? If there are, then do we have to take care of them? No? Yes. I think yes. I equals 1, I less than equal to n, I plus plus a dj I equals 0. Like we don't take those roads. The road not taken because we are already there. So if that is the mistake, that is they might be giving queries where we are going from this, our target city is same as our starting city. So that might be the mistake. We have fixed it. So this should work, hopefully. Okay, testing. It does work. It does work. So what have we done? We have done Floyd-Warshall, we have done Dijkstra's algorithm, we have done Bellman-Ford algorithm. And what have we learned from doing these things? What do we know? Finding shortest paths. And we have 3 algorithms for these. One is Bellman-Ford, and there is also shortest path faster algorithm, which is a variation of the Bellman-Ford algorithm. So we can write that in smaller. And then there is Beats, which would I would have to see the spelling. D-I-J, D-I-J-K-S-T-R-A, Dijkra, D-K-S-T-R-A, Dijkras. Dijkras algorithm, Freud-Warshel algorithm. And we also have, yes, Freud-Warshel, YD, Freud. I think it is S-H-A-L-L. Uh, what is it? Floyd, S-H-A-L-L. So we have these three algorithms to find the shortest paths, and they have their nuances. That is, in case of these two, the distance that we get is only for a single source, a red. Yeah, these two only work for single source, but this one, Floyd Warshel, works for uh, all pairs, and that is very nice about it. But the time complexity is also, let's write their time complexity. Time complexity for Bellman Ford is big O of n into m, make that smaller. Yes. And for Dijkstra, it is it is n into or n plus m log m. Yeah, because we are going to each vertex once, and we are also going through each edge once, and not even once, we are going through a edge multiple times. And to, in our like priority queue, the time complexity to get the shortest current path is log. So that is why this is the case here. And in this, the time complexity is n cube, and that is all. That is all. We have done this. That is very, very nice. Let's go through the implementation ones. So I, J, I equals 1, J equals 1, and distance is just minimum, and that makes sense. Yeah. If Ij equals then this. Otherwise, um, if there is a edge, else if ADJ, AJ, if there is a edge between these two, then we say distance Ij equals distance ADJ Ij. Yeah. Okay. Okay, cool. The time complexity of the algorithm is n cube because it contains three nested loops that go through the nodes of the graph. Since the implementation of Floyd-Warshel is simple, the algorithm can be a good choice even if it is only needed to find a single shortest path in the graph. However, the algorithm can only be used when the graph is so small that a cubic time complexity is fast enough, and that was very good. So we have gone through the shortest path algorithms, and that is very nice. At this point, we can implement, and we do understand all of these three shortest path algorithms, and that is very nice. Freud-Warshel, Bellman Ford, the first one, then shortest path, faster algorithm, then Dijkstra, and then Floyd Warshall, and that is very nice. And now the next thing that we have is tree algorithms. Tomorrow we are going to do tree algorithms, and that will be nice. What do we have in tree algorithms? Tree traversal, dynamic programming, diameter. For finding diameter, there are a couple of algorithms, all longest paths in a tree, and binary trees. Okay, cool. So that is kind of cool. We have gone through that mm, chapter in CPHV about finding the shortest paths, and we have learned three algorithms for finding the shortest paths, and that is it for today. And thank you for being here. Bye. That would be the end of the stream. Thank you for being here.